In this video, I'm going to hopefully go through a few analogies or models that might help you understand how infrared spectroscopy works. Infrared spectroscopy is a way that we can find what chemical bonds are present in a molecule. And basically what you're doing is you're passing a wide variety of wavelengths or frequencies of electromagnetic radiation through a sample, and they are all in the infrared range. So that's above about 750 nanometers in wavelength, up to about 4,000 nanometers in wavelength. So it's quite a big spectrum. You're passing all of these through a sample and finding out how much of that radiation is absorbed and how much is transmitted through. And the reason that it transmits or absorbs is to do with the chemical bonds in your sample. Alright, some chemical bonds will absorb certain wavelengths while having no effect on other wavelengths of infrared. Alright, to show you sort of what I mean, I'm going to start with something you're all pretty familiar with, a Raybox and a filter. So the Raybox is giving off white light, so visible light. We'll ignore the fact that it's hot, so it's giving off infrared as well and all those other things. But it's giving off white light. And we know that the visible spectrum has got a range from about 400 to 700 nanometers. That's our blue at 400 to red, which is 700. All of that light is being transmitted out of here at the moment because there's nothing in the way. But if I was to put a filter in front of it, then only the red wavelengths can get through. So what's being absorbed by the filter, so our sample, if you want to think of it like that, are all of the wavelengths except the ones around about 700. They're actually getting through. So if I had a graph to show the absorption, then I'd have lots and lots of colours being absorbed, and then I'd have this bit of red, around 700, where none of it's being absorbed. Okay, same idea with the blue. If I put a blue filter in front of it, these are primary colours, by the way, which is why I can pretty much guess their wavelength. Blue, primary blue is probably around about 400 nanometers, maybe a little bit below that, a little bit higher than that, maybe 450. I put that in front. Again, this will absorb all of the wavelengths of white light, but let the blue through. So if I had a sensor out here, it would only pick up the blue wavelength. And we could use a white bit of paper as our sensor in this case. Alright, however with infrared, that's a wavelength we can't see, so our sensor has to be something else. Alright, so what it does, it finds which wavelengths of infrared get through and which don't. Also, your sample isn't going to be a filter like these coloured filters, it's going to be a solution of an organic chemical usually, alright, which has got no colour, and so that's why we don't use the coloured wavelengths, because that'll get through. However, if we use infrared, we find that they do actually, some do get absorbed by certain wavelengths of infrared. And the reason for this is a thing called resonance. All chemical bonds, rather than being rigid like you imagine with your little plastic models that we make of molecules, they're more like, if you think of it like a spring. It can twist, it can stretch, it can compress. Okay, so chemical bonds are basically doing something like this all the time. And they have what's called a natural frequency. So if I just look at the spring quickly, and if I was to bounce the spring and wait for it to naturally bounce, it's got a natural frequency. And a bond has a natural frequency that it will resonate, or sorry, not resonate, that it will bounce at basically. If I was to pass any wavelength or frequency the same as that through the sample, it will make it resonate. And that means basically it's like double bouncing on a trampoline. Okay, when you bounce on super high, that's simplistically resonance. Okay, another way to show it is if I was to hit one of these and have nothing in the way, then all of that sound is travelling through. Okay, if I was to put my hand in the way, it still all goes straight through because that's not happening yet. Because my hand isn't at that frequency, so it's not absorbing any significant amount of that. It's absorbing some because it's energy, so some of it's going into my hand, but because it's not a resonant frequency with that, the majority of that sound wave just carries on. So if I had a sensor over here, it would pick up the majority of that sound energy. Only a little will be absorbed by my hand. But if I put something in front of it which has the same natural frequency, we know that because they're the same size, then we end up seeing that quite a lot of the energy is not going to be transmitted, it's actually going to be absorbed by this. And the way we can do that conveniently is with sound. You can hear that this one's actually vibrating as well. So it's used quite a lot of that sound energy to create vibrations. So what we'd see is, compared to my hand, which lets most of that sound wave through, in this situation, this actually absorbs a heck of a lot of that sound wave. So we'd see a downward peak on a graph that was showing the amount of energy getting through. Okay? I can change this very simply, by the way, once I see where I put my blue tack, or green tack in this case. If I put a bit of green tack on this, it changes the length of one of those. So now let's see what happens. Just by making a subtle change, that frequency no longer is being absorbed by these tuning forks. It's just being transmitted straight through. Another good way to show you resonance is actually with a spring, because this is very similar to what's happening with a chemical bond when we put infrared through it. So what we've got set up here is an electromagnet, so just a coil, connected to a power source, and it's on AC. So basically it's on, off, all right? And it's going to be on, off at a frequency that I can play with. I can mess with that, okay? And I've got a spring, which has got a natural frequency, as we saw before. Now, if I send through, if this is going at the wrong frequency, so if it's not the same frequency as this is going to bounce in all sorts of funny ways. So if we think of this as our model, that means most of that wavelength of infrared is just going straight through. It's messing with the bond, but not enough to actually be absorbed in large amounts. Some's being absorbed, but not all of it. Or not a large portion, I should say. If, however, I hit the natural frequency of the spring, it will start to resonate, and you'll see what that looks like. I'm not going to give that away yet. That means the majority of that energy in infrared would be being absorbed. Very little would be getting through to our sensor. And so we'd see a big peak at that one. And there's a typical one at about 3,000 to 3,500 for the carbon-hydrogen bond. And you'll see that quite regularly. So let's see how this looks. Just make sure everything turned on there. And by the way, I've got another spring, so I can show you that each spring is different. Okay, so at the moment, you can see that it's not bouncing regularly. It's all over the show. So that means whatever frequency I've got this on is not quite its natural frequency, so it's not resonating, it's just bouncing haphazardly. Alright, so I'm going to go down to 1, and I'm just going to slowly move it up, and I think I'll be able to guess, mainly because I've played with it before, guess where it's going to actually resonate. Now here you can see it's starting to really bounce, and I just moved it a little bit, pretty much uniform, not quite there yet. There we go, it was going crazy there, so. And it's not about turning it up to make it bounce more. There we go, I must have got it. Must have got the resonant frequency because it bounced enough to get off. It's not about turning it up higher and higher to get it right either, by the way. I'll turn it way up and show you that it actually doesn't have much effect at all. Okay, that's on, it's just doing nothing. It's a higher frequency and it's hardly jiggling at all. Okay, so it wasn't about the fact I was adding a higher and higher frequency. I went higher and higher until I hit the resonant frequency, and then it went crazy. That's where it's absorbing, if it was a chemical bond, absorbing that particular frequency of infrared. Yeah, same again. Alright, now each chemical bond is unique, and that's why this method works, because each chemical bond absorbs a different wavelength of infrared. So, I'm sorry, this is going to take me a couple of seconds to set up, mainly because this hits the ground when I put it in. Apologies for the annoying sound. Okay, so here I've got a different spring, so it's representing a different chemical bond. And I've still got it at the resonant frequency of this one, and you'll notice it's doing very little. Okay, if I change this frequency, And again, I'm just going to go up because I know from experience that it's not below this. If I go up with this, we'll see some changes happen with the spring. So again, some is being absorbed. Some energy would be being absorbed by this chemical bond, but most of it's being transmitted, going through the sensor. I thought it was around about here, so might have been wrong. No, I was wrong. It's a lower one. My apologies. Must have started with this one. There we go. You can see it's starting to get quite a bit of a bounce on. Alright, so I've managed to find the resonant frequency, and it's about 1.1. In this case, it's 1.1 hertz because it's not been amplified much. 1.1 hertz lower than the other one. Okay, so I actually think it's a little bit shy of where it should be. There we go. You can tell I hit it now because it's hitting the bottom. Okay, it's really. Alright, I might turn it off before it noises too much. Alright, so each bond absorbs a unique little band of frequencies. Alright, absorbs the energy there. Another way to show this, and the last way I want to show you, is this. Also to show that there's absorption happening even if that isn't the bond that is resonating. Okay? What I've got here, I'm sorry, I've forgotten the name of this pendulum system here, but if I swing this pendulum here, it will only have an effect on the one that is the same frequency as it. Sorry, a resonant effect. But it will actually have an effect on all of the others. The reason it does is they are actually connected at the top. It's not magic. Okay, they are actually connected at the top by a string. Alright? So if I swing this one, I hope that doesn't hit the wall too much, then you'll see it starting to move the other ones. Okay? But one in particular is moving a lot more. The one that is the same length, which makes sense because we're looking at frequency. So this one here is about the same length, and you'll see it's moving a lot more than the others. This shows why in the spectra, at every wavelength, there's going to be some energy absorbed. Because every chemical bond is going to absorb a little bit. But this one here is going to absorb a lot of that energy. So you're going to have a little bit, large one, little bit, for your absorption spectrum. Because all of these are being affected a little, but one of them is actually resonating because of it. So that's a couple of models to sort of understand how infrared spectroscopy works. The infrared wavelength is actually quite a large group of waves, and we use those by firing them at our sample and seeing which ones are absorbed and which ones are transmitted. The ones that absorb tell us that tells us those chemical bonds are present in our sample. We then combine that information with other stuff, so other spectra, mass spectroscopy and nuclear magnetic resonance, to work out what that compound is. Thanks, Sam.